Friction is a force that's going to oppose motion, any force really that's going to oppose motion. So let's picture if we're trying to push this block along this surface here, there's going to be a force that is acting this direction. We could call it maybe force of friction that's going to try and prevent us from moving this. There's two types of friction. There is kinetic friction and there is static friction. Okay. Kinetic friction is the friction that you experience while something is in motion. And static friction is to just get it moving. Okay. So, you have to push really, really hard to get something moving, and then once it's moving, because it has some momentum behind it, some inertia behind it, it's going to be a little bit easier to keep moving. So usually, kinetic friction is going to be a little bit less than static friction, right? We have to push really hard to get it going, then once it's going, we just have to kind of nicely oppose that frictional force while it's moving. Friction comes from having two surfaces rubbing together. So if we were to look really closely at what friction looks like, we might see something along the lines of this, where we have our direction of motion or attempted motion going this way, and then friction force acting that way. Well, when we look really, really closely at the surfaces actually aren't smooth. Even the smoothest surfaces that you can think of have these little ridges and bumps, especially when you get down on a, maybe even a molecular level. And so when these bumps rub up against each other or push up against each other, usually due to like an electron repulsion even, it's going to impede that motion. It's going to slow it down. So that's where friction actually comes from, is the rubbing of those two surfaces together. So next thing we would need to figure out is how do we actually calculate a frictional force? So to do that, we have to think of what matters when it comes to friction. Okay. Well, one thing that matters that's kind of obvious is the two surfaces that are in contact, right? If I have my one surface here and my little box pushing along, if all of a sudden instead of pushing this box along, maybe a gravel surface, now I push it across ice, there's going to be a difference in the amount of friction there. So those two surfaces that are in contact matter. The other thing that matters is the normal force, or the weight of the object that's pushing down on it, right? Because normal force is going to be opposite of that. So if we have our force of gravity pushing down here, the weight of the object, the more an object weighs, the harder it's going to push against that surface, and that's going to push those little bumps and things closer and tighter together and make it hard to move. So a greater normal force, since normal force is opposing gravity against the surface, the greater our friction. So our two equations to calculate friction look like this, and we'll start with kinetic first. So for kinetic friction, we're going to say Fk equals mu k Fn. And this mu k here is what we call the coefficient of friction. Now the mu k is a part that we were talking about when it comes to the two different surfaces in contact. For example, a block of wood against gravel, a block of wood against ice will have different coefficients of friction. So this is a number that maybe you're looking up in a table, or maybe it's the number you're calculating in the problem, but it's not a number that you're expected to know by any means because it's unique to every single combination of surfaces. The equation for static friction looks very similar. Mu s Fn. So almost identical, right? We have another coefficient of friction here, but this time it's a coefficient of static friction. So even for the same two surfaces, our coefficient of static and our coefficient of kinetic friction might be two different numbers. So that's why we kind of write them out separately as two different equations. But those are the two equations that you can use to calculate a force of friction. Okay. Drag force is another sort of type of frictional force. Another way to think of a drag force is we're talking about air resistance here. Okay. Not always moving through the air. Maybe it could be something through water or some other fluid or something like that. But air resistance is a really good example of a drag force. So if we think about a drag force, what would matter in the drag force? Right? In other words, if we're calculating a drag force, what would we include? Well, you wouldn't guess this one, but we do include a 1/2. The next thing you might think of is, well, the two things that are in contact, or the shape of the object, things like that should matter. And that all factors into something called a drag coefficient. So that's C here. We call that a drag coefficient. Similar to our coefficient of friction, in that it's something that's going to be unique to objects. A density, that we use the Greek letter rho for, and this is density of the fluid that we're in, so a fluid density. Now, don't let that word fluid trip you up. We haven't talked about it a lot yet, but air is considered a fluid. Gases are considered fluids. Okay, so really anything that anything is going to be moving through is going to be a fluid. Capital A for area. And that's the cross-sectional area that's trying to sort of push through that fluid. So you can think the bigger area we're trying to force through the fluid, the harder it would be to do, so the more drag force you get. Think about like a skydiver going horizontally down versus feet first, right? Feet first has a much smaller area, so much less drag. And then velocity squared. So that's just our usual velocity. Okay. And velocity, because the faster you go, the faster you try and push through that air, the more it's going to try and resist you because it has its own inertia that you're trying to work up against. So that's how we'd calculate a drag force. In general, for most any problem, friction forces, drag forces, these forces, our friction and drag, are just going to be included in a Newton's second law application. So sum of our forces equals mass times acceleration. And our frictional forces are just going to show up over on this side of the equation where we're putting all of our forces together. Remember that they're a vector, and friction is usually opposing motion, so it's usually going to be a negative force, right, when we add everything together.